Hello, Internet friends. Chris Masto here with part 2 of the USB power on delay circuit. In the last video, if you saw it, and if you didn't, you should probably go watch that because this one won't make much sense without it. I showed the schematic for this circuit, which I came up with to delay the power out to a USB device after the power in is turned on. And while it technically works, I made a couple of mistakes here, and I wanted to go over that and what I'm going to do to revise it to get rid of those problems. So the big one here is, if you recall how this works, the power comes in here on the left side. So there would be a USB socket somewhere that would have, I can't draw very well here, but USB socket that something would be plugged into. And then on the output side, there would be another USB socket that you'd plug your device into. So whatever you're running here, let's call your old school iPod, would be plugged into here, and that would get the power. So what happens here is the power comes in through the USB socket into your device and then back out and goes into here. And this MOSFET right here is the thing that switches to allow the current to flow through and reach its way to ground. So when this MOSFET is switched off, then this is blocked here and the current can't go and your device doesn't run. So what's wrong with this? Well, the big thing that's wrong with this, and thanks to my friend Jordan for pointing this out, is that I'm doing what's called low side switching here. So this device, if you think about this as the voltage up here is 5 volts. So this is the high, and the voltage down here is 0, which is lower than 5. So the switch here is on the low side and the device is on the high side. Well, this means that this 5 volts here is always live, right? It comes in on the left here and flows all the way through and flows out to your device. On a circuit board, there are a lot of things that switch this way. For various technical reasons, it's easier to build something that uses a low side switch like this. These kind of transistors don't require as much circuitry to switch on the low side as they would on the high side. So I just sort of did this because it was familiar, and also because this is the only part that I had in my parts bin, and I wanted to use things that I already had here rather than have to buy something. But you really don't want to do something like this when the power is leaving the circuit board and going to an external device. The reason for that is because, let's say, where does this power come from? Like maybe you're using this little box in your car, right? So I'm going to draw a car here for some reason. So the power is supplied from the car and the ground returns to the car. Now this USB socket is going to be made of metal and so on. It's connected to the ground reference for the car. So it's quite likely, I'm going to redraw the car over here just to make my diagram a little bit easier. So it's quite likely that your car is referenced to ground. There might be other devices that you have attached to this device as well. And so you're going to have this 5 volts that comes in, and it can't get to ground through this MOSFET because it's turned off. But who's to say that it can't get to ground because it's also connected to your car, and your car is connected to ground, and so it might find a path through there that doesn't depend on this delay circuit being engaged. So whether this works or not in a given situation probably depends on a lot of things, but let's just say that this is probably not a good design for the thing we're trying to do. One solution to this problem is to get rid of the low side switch that we have here and replace it with a high side switch. So instead of a situation like this, where you have your voltage at the top, and then it goes through the device, and then it goes through some sort of switching device to allow it to flow to ground. So what we could do instead is have the switching device on the high side and the load on the low side, and then all should be well, right? Well, yes and no. Like I said before, it's technically pretty easy to drive a transistor on the low side. It has to do with the voltage going in to control it being higher than the voltage coming out. And that's easy to accomplish here because you have access to your 5 volts or whatever right here. And this point is referenced to ground. 5 is more than 0, but here you don't have that situation. So let's say you've got your 5 volts control voltage coming in. Well, this point is also going to be at 5 volts when this thing switches on. Sorry about my ugly 5s. You can't simply relocate this part and expect everything to work. There are some techniques to work around this that involve driving it with a higher voltage. You could also use a different type of transistor, which you would probably do anyway, but that also requires more circuitry to drive it. There's a much simpler way around this problem, which is throw this thing away entirely and replace it with a dedicated part that's designed for doing exactly this. So that's what I'm actually going to do. Let me show you. Here's the new schematic. What we've got in this one is this box in the middle. This is the TPS 2024P from Texas Instruments. It is literally designed for switching power to USB devices. It takes an enable signal in here and it controls whether the power is supplied on the output. And it is a high side switching device. So on the output here, this will go to our USB port and then the device will be connected through there to ground. It's different from what we were doing before, because the power coming in is the thing that's switched on and off instead of the ground coming out. Remember, before we had our MOSFET in this area, but this time we have the power supply coming in, which is being turned on and off by this chip. It's a very simple, inexpensive chip. It's very easy to control, very easy to use, so that's what we're going to use for this. As a side effect, it actually improved some of the rest of the circuitry. You might notice I'm only using one op amp this time. The reason for that is related to this bar here over the enable signal. This designates that it's active low. Active low means that when you give it a 0 signal in, it turns on, and when you give it a 1 signal or 5 volts in, it turns off. So it's kind of the opposite. Because of that, I had to rearrange this op amp. Remember, the way it worked before was we had a threshold voltage and then this capacitor would charge up, and once it went above that threshold voltage, then the signal would go from low to high, turning on the MOSFET. Well, now we need it to work the other way around. We need our output signal to start high, and then when this crosses the threshold, it goes low. Now that's somewhat trivially accomplished by switching the inputs to the op amp. If you compare this to the schematic we had before, the inputs are swapped. The voltage from the capacitor charging up is going in here to the inverting input, and the threshold voltage is going in here to the non-inverting input. A side effect of that is that this feedback here for the hysteresis is now associated with the threshold voltage rather than the voltage from the capacitor, which means that this goes straight in. It's not affected by any resistance, and we don't need a buffer anymore. Now, I don't have this chip, so I'm going to order it from DigiKey. It should be here in a couple days. And once I get it, I'll probably do some little experiments on a breadboard to make sure it works the way I think it works. And then finally, we'll build this into a finished product. So expect more videos soon, and don't forget to like, comment, and subscribe. I will see you next time. Bye.